Okay, good morning, everybody, and would like to thank the organizers for the invite. My name is Marwan Jabri, and I'm with Neuromorphic LLC, and my talk today is about biologically inspired and supervised learning of higher order visual features. A bit about my background. I designed and built learning neural chips in the 1990s. Maybe the most memorable of those, for those in the audience that would remember those days, is the master perturbator chip, which basically does online on-chip learning using perturbation techniques, which is a technique, maybe it's not well known these days, but I encourage people that have been looking at analog and mixed mode implementations to actually look at them, because they are way more economic to implement and more friendly to analog implementations. The work I'm presenting today is based on collaboration I've done with Terry Sejnowski in the 1990s, and this work was really focusing on sensory motor control. It builds on large body of literature. Of course, the Neocognitron, HMax, and many others. And prior to that, I've done some work on modeling the MSTD, the medial superior temporal dorsal area using independent component analysis. So about Neuromorphic is an early stage startup developing a smart software agent. Our first product, and this is a plug, of course, is a Neuromorphic Smile, which is a speech recognition-based picture annotation. So you can take a photo, speak in the microphone, the voice is converted into speech, into text, and is inserted into the photo, and you can search your photos using normal text search. And we're currently developing a sensory motor integration control agent, of course, software-based agent. So the presentation today concerns how you can extract higher order features in the visual space, with the application that we are focusing on being in the sensory motor integration and control, obviously for robots, and more specifically for home robotics. So the visual object recognition is targeting mainly body parts and, more importantly, faces, whether they are still or moving. The approach we have taken, which is biologically inspired, has a number of advantages, and I think some of them will become apparent during the talk. One of them is that it gives you pieces that can be reused for various tasks that you would like to do during sensory motor control. The task we are looking at involves pose-independent, luminance-independent recognition, and that's fairly important in terms of the use case we are looking at. And another important criterion is that the system has to learn incrementally and nearly in real time. Nearly in real time meaning that it should take at the most a minute to actually learn something and basically incorporate that into its capabilities. The model we will be presenting is the actual feature analysis, and to test the goodness of this feature analysis, we basically label the features or the collection of features using a shallow network that is a two-layer supervised learning-based neural network. So most of the feature analysis is done using an unsupervised learning method, whereas the actual labeling of the resulting features is done by a labeling system, which is effectively a two-layer multi-layer perceptron classifier. So here I show the architecture on the left. You have the system, the visual processing pathway system. It's nothing mind-blowing about it. So we do some pre-processing on the pictures. We do some part detection, faces, other body parts. We then do feature analysis. We do some classification, some post-processing, and then you have some output labels of the objects. On the right-hand side, you see the feature analysis part, and this is basically the biologically inspired part that we're interested in today. So you start with an input image at the bottom, and then you go through a number of modules that are biologically inspired, starting with an area that represent, V1, going through an area that represent V4, which is specialized in part detection, and then going through the posterior IT, then the anterior IT, producing features at the output. And in the system, these features go then through the classification, which is shown here, and then the output of the classifier go through a post-processing, producing some final labels. So this is another view of the system. So you have the input image. The first two layers, you can think of them as being the first two layers of HMAX. You have the bank of filters. These are pre-computed Gabor filters. Then going through a max pooling layer, the V1C layer, and then go through a V4 layer, the V4 module that has two sublayers in it. The first, what we call the integration layer, and this is basically a lateral interconnected self-organizing map, and I will go into the details of this in a minute. This feeds into another pooling layer. The output of this pooling layer goes through the posterior IT and then through the anterior IT. So in terms of complexity, you will see that in a minute, but that's basically the flow. And the max is simple max computation. These are pre-hardwired, so the learning effectively is happening in this layer, and this layer, and this is all unsupervised learning. So an easier way to actually see the architecture is through a textual description. So we're dealing with 8 orientations for the Gabor filters, and then you have the simple V1. This is the bank of filters, the Gabor filters, and then this is the complex cell layer, and this is basically showing how the pooling is working. So the first pooling is happening on the 7 and 9 filters, the second on the 11 and 13, and so on. Then the integration layer of V4 is basically taking all the orientation, all 8 orientation sheets of V1C and integrating them into a single sheet, meaning a single map representation. So you have, in this case, 8 maps. Each map is integrating all 8 orientation of the V1C output. Then, after this integration, you have a pooling that basically happens on the integrated sheet. So it takes 2 sheets at a time and it pulls them. This pooled representation is then integrated further to extract higher order features by the equivalent of PIT. And this produces 2 maps, and these 2 maps are then used to learn a higher level of representation representing AIT, and obviously it has a larger receptive fields. So in this picture here, you see the relative size of the receptive fields on the face. So the gray part in the inner is basically V1S. The bluer circle is V1C. The green part, the green circles are V4. the yellow are PIT, and red is AIT. And these sizes of receptive fields basically have been, based on physiology results that basically have been reported over the years. So obviously, in physiology, you have a wide spread of sizes of receptive fields. So basically, we took some sort of an average for these receptive fields. Obviously, through the learning, the receptive field can start large, and the learning can basically tailor it to what the correlation basically, the correlation that develop. So in terms of the sizing of the architecture, all the sizing that we work with are based on some densities of neurons per unit. The unit is 1, of course. So the retina density we start with is 196 by 196. Then you have up to 128 sheets of V1S, each at 196 by 196. We ignore padding for now. And all these Gable filters are pre-computed. Then the pooling layer of V1C has up to 64 sheets, and each of 128 by 128 density. The V4 integration sheet have 196 by 196, and there are up to 8 of them. And these are the laterally interconnected self-organizing map. The pooling layer V4M has lower density, as you would expect from a pooling layer. And then the PIT sheet has a reduced density going from the 128 by 128 to 48 by 48. And the ART sheet has similar density. So the laterally interconnected self-organizing map, there's quite a large body of literature on this. This is really a version of it that basically evolved as work has proceeded on this. And what you basically have, you have an input sheet, which is named here TX, a target sheet, which is the RX sheet. And this is a sheet of neuron at specific density. And then each neuron in this sheet basically has a receptive field on the input. The darker gray one is one of these receptive fields. And then this neuron also has a laterally connected receptive field, basically consisting of an inhibitory one, which is shown in red, and an excitatory one, which is shown in blue. So in terms of terminology, obviously the afferent is basically the neurons projecting from the lower layer to the upper layer, and the lateral are, when I mention lateral, it means both the excitatory and inhibitory. In terms of learning, the learning is, having implemented chips in the past, my goal is always to actually keep it as simple as possible to ensure that this is something that can be optimized at some stage in hardware. So the learning, basically you take the input, which is shown here in the circle, it goes through the weights, and the sum is produced, giving you a quantity as net I, and then this quantity is basically put together with the lateral input. So this lateral input is in net I as well, and then an output is produced. And then you have a number of iterations that basically happen in order for the output to settle. And this number of iterations, based on experimental work that's been done by my team as well by many others, show that it's rather quick, anywhere from 4 to 8. So we basically pick a maximum of 16. If the settling has happened within the 16 iteration, then it's fine. Usually it happens in few iterations. So once the output has stabilized here, we basically have this output of this neuron, and the weight update is a straightforward Hebbian, which is shown here, and we use just weight normalization to keep the weights in check. So all 3 layers, which are based on this are basically implemented this way, and the actual implementation is the actual computation. The bulk of the computation is done in parallel C, So it is running on as many cores you have in your machine. But the overall framework is implemented in Python within the Topographica simulator. So all the experimentation is really done in using Python. The visualization is done using Python, and you will see some of the visualization in a minute. But most of the computation, whether it is dot product, max, etc., these are all done in a parallel implementation. So here I show after learning, and what you can see here is the output of, so this is from the live faces in the wild database, the late Ariel Sharon here, and this is the retina, this is the V4M, the pooling layer of V4 output, and this is the V4 activities that basically is produced. So I did not show V1. These are straightforward gavers, so I'm just skipping those. And as you can see, you know, the larger filter, which is shown here as F13, dominates the output. This is the smaller filter, which is the F11, and the V4M is pooling these two and producing this picture. And the blocking that you see here is the typical blocking that you see in a pooling layer. So this is the features that have been learned using in this laterally interconnected self-organizing map. These are the two maps. So this is another example output. This is another example output. So all these are from live faces in the wild database. So this is showing the receptive fields of V4I. The receptive field of V4M are fixed. These are the max operations. And this is a subsample of these receptive fields. So this is not the full array. And as you can see, you have parts that basically been extracted. If you look closely at those, you will see that these are typically variations of things like lips, parts of eyes, and so on. And if you look at you have to look at it this way, and this is showing all the receptive fields that have been produced through this Lisum learning in V4I. So obviously, the integration layers are operating on 8 orientations. So this is the 90-degree orientation. So these, you will see features that are, these are parts that are observed, correlated, extracted in the faces and from various angles. So it's 90 degrees. This is the 112.5 degrees, and so on. So I'm not showing all of them, but that's basically what you end up learning in V4I. So the next layer, PIT. So here you see the responses of the PIT layer after learning, and this basically showing the V4M input to this layer. And as you can see, the responses is still topographically aligned and oriented, meaning that you can see the topography of the input picture in it, which is normal for PIT, as this is looking at receptive fields in the size of anywhere from 5 to 8 degrees. So that's normal, and it reflects what we know from biology. This is another output of after learning, another output. And these are the receptive fields. So the receptive fields are fairly different from PIT. This is a sample of them, and you have to look a bit closer because some of them are faded. But if you examine these receptive fields, you see that they consist of more complex parts that are seen in faces. And this is a sample. This is the complete receptive fields. You have to look at them that way, and you still can see that there's the topographically aligned face-looking thing overall in these receptive fields, which is also expected. This is the inhibitory receptive fields. This is a subset of them, not all of them. And as you can see, the inhibition is still working on a topographically oriented way. The extent of the receptive field for the lateral inhibition as well as the excitation, these have been really the most challenging part in the work that's been done. It's basically trying to work out something that is anchored in neuroscience, but yet at the same time consistent with the problem we are working with. Now, for AIT, so this is the responses of the model. And here you see that the topography is completely lost. All what you see are a bunch of cells that go active, that have learned to become active for this type of phase, actually for this phase in particular. You see on the left the PIT activity, on the right the AIT activity, and this is after learning. This is another version of the same phase, of the same person, another phase, another phase, another phase. So here we show the receptive field, the afferent receptive field of PIT, and from PIT to AIT. And here you see effectively, if you examine these receptive fields, what you see is something that looks like a face, with various types of features in them, basically covering areas to do with the eyes, a little bit of the nose, the mouth, and this is just a subsample of the totality of receptive fields that we have. So the actual array of receptive field is 48 by 48, of course. There are as many of these. So this is the lateral inhibitory receptive fields that basically develop during the learning. And what you see here are basically the receptive fields, large initially, and then as learning proceeded, basically every area becoming more specialized toward the inhibition that is needed to make this feature detector basically become more tuned. Now, I haven't mentioned the excitatory part of the receptive fields. So all the excitatory receptive field that we worked with have been fixed. So the only part that is learning is the inhibitory receptive field. And basically it's a Gaussian type receptive field. So we analyzed this model and some interesting things to note is that the LISM with Hebbian learning for all three layers, V4, PIT, and AIT, basically develop tunings and feature detections as you would expect for the type of complexity of features that basically are at this layer. So V4 becomes tuned to parts at various angles. PIT becomes tuned to more complex parts at various angles, various orientation, and AIT becomes more tuned to complete faces at various angles. So what is basically showing is that the LISM learning is effectively extracting the type of features based on the architecture that is being used, and importantly the lateral inhibition and the competitive nature of the learning that is happening in these layers. Now, to test this, we actually take the output of AIT and put it through a two-layer multi-layer perceptron. So this is basically to recover or to get the labeling of the output maps of AIT and see whether actually this is representing in some unique way the faces that basically we have learned on. And so to actually do that, given we're dealing with very large network with limited resources, so basically to train the complete system, we basically train it in stages and we record the response. And then we take these responses to basically train the next stage. And that's basically how the complete model is learned. So we don't have to load the complete model in a machine and learn it all in one go. And we tested this system on both proprietary database that we're using for our use case, as well as the LFW database. On our proprietary database, the testing error rate was less than 5%, and this is on a fairly challenging database in terms of luminosity and pose invariance of the same person. On the LFW database, we basically achieved on the training part is 99.68%, and on the testing part is 88.81%. We haven't put really much effort in terms of optimizing it for the LFW database or any other database to that matter. All the focus really has been on the use case that we have been developing, given that the nature of the images that you work with have direct impact on the performance and the system you end up with. So to summarize, a biologically inspired unsupervised visual feature extraction to develop receptive fields that are tuned to parts, complex parts and faces have been presented. To test the model and its effectiveness, we use a two-layer multi-layer perceptron to basically do the labeling, and it shows that we end up with very respectable classification outcome. The receptive fields of the model can be visibly interpreted, meaning you can look at the receptive fields and find what you expect and look at the variation that you basically have. And this is an interesting property of this model. The responses of AIT are sparse, but they are not as sparse as we would like them to be. And this is an area that basically we're looking at in more detail. The actual layers, V4, PIT, AIT, themselves can be used for other type of image processing, as well as machine vision applications, whether it is for segmentation, figure ground processing, and so on. And if you want to do labeling, well, we use a multi-layer perceptron, a two-layer multi-layer perceptron to do labeling, but the intention is actually to go beyond that without having to actually use a multi-layer perceptron, and this is work that's in progress. From all the work that we have done, we found that actually the biggest challenge in this is to look at the lateral interconnections, the inhibitory receptive fields and the excited receptive fields and the parameters of these fields. And there's very little data in the neuroscientific literature about the extent of these receptive fields and the properties of these receptive fields. And this is an area that really would like to see much more data on. Thank you. Well, okay, so there is, you can look at this from two perspectives. And in one sense, if I answered your question correctly, in one sense, you would like to see whether these components that makes faces, right? In our case, and I think as you go higher in visual cortex, I don't think you're basically looking at and components that necessarily are not specific to specific faces. So when you go to AIT, the question of whether you look at having filters that really detect any face versus filters that basically detect specific type of faces, or I mean specific pose even in the face with some rotation in various of some sort. But the data, the neuroscientific data basically shows that you have different cells that respond at different poses at various angles, and this is basically what we find in our model with no tuning to that effect. So from that perspective, I think the result that we see in AIT is in line. The earlier layer, V4, there is very little indication on whether this pair of, this this eye is for this person or for that person. What you see is basically pieces that have been integrated during the learning, and many versions of it basically being extracted due to this competitive learning that's taking place. So I think in the earlier layers, you have more invariance, but as you go higher, you basically expect to see more specificities, and that's basically what we found as well.
Yeah. Would you be able to provide any comparison with most these general purpose deep learning networks image categorization in your system?
Well, we haven't really looked at comparing this with DeepNet. I mean, our purpose has not really been to do a face recognition system and that's it. Because if you want, all what we wanted to do is a face recognition system, we probably have done it totally different from that. So the intention has always been that, you know, we have some specific requirements per our use case, and this includes motion gesture detection by body parts and so on. And for that purpose, basically the architecture that we have done is the most suited for that purpose. But we're going to be looking at comparing it with other type of systems, including deep networks, for categorization purposes.